Okay, so if you remember, what we're doing here is slowly closing the box and developing some ideas that we need to talk about observations and to ask questions about how much we can learn from observations. When we're doing the dynamical systems, in a sense, we got to see the state space and see the trajectories, see the attractors, and that's sticking our head inside the box. What we did last time was maybe the last point where we have our head inside the box, because we were talking about how dynamical systems pushed probability distributions around. Right? We shifted from starting from a single initial condition and tracing an orbit to starting with initial distribution and looking at how the dynamic pushed a distribution forward. And there was something new there, because now a distribution not only has states in its support, but attached to it, just like the Poincare stretching, the pixels had colors attached to them and got pushed around. Now probably the distribution has states in its support, but probably amplitudes. And we had to worry about how those amplitudes got mapped forward. And that had everything to do with whether things were stretching or folding. So today, we're going to talk more directly about representing time. Last lecture was how distributions got moved forward, but at each moment in time we were looking at a distribution over the state space. Now I want to talk about behaviors or sequences of behaviors. And we'll do it in a slightly simplified form today. Last time we were talking about dynamical systems with probably distributions over continuous state spaces. And today we're going to talk about processes over discrete state spaces. And then next lecture we're going to bring these two things together with this picture of an instrument providing a coarse-grained representation of continuous internal states. So all three of these lectures sort of knit together into what I call sort of measurement theory. We need to know how probabilities slosh around in the dynamical system. Today we're going to talk about what happens if we had discrete precision, finite precision measurements and their probabilities and how we represent those. And then that kind of, the two lectures leave this question hanging out there. Well, how are these connected? And we do that with this technique called symbolic dynamics on Thursday. So then that will set us up to start talking about information. A quick comment at the end of the lecture notes. There's some slides which I'm not going to cover in lecture and we won't use, but there's a technique that lets us calculate distributions on discrete symbol models called Z-transform. So you can just ignore that for now. I'm not sure that we'll use that directly. It's a very useful calculational technique, but for our purposes now, maybe a little bit of a distraction. Okay, so we're marching along here, marching along the measurement channel. So like before, we're introducing actually a new set of ideas. Depends on our remembering some of the probability theory we've introduced before. But now we want to talk about chains of random variables. Namely, looking at a system as it's unfolding over time and imagining we're measuring the system at a sequence of times. So typically, we'll think of this as discrete time measurements. We have a random variable at each time. And there'll be some shared alphabet for the random variable across the different times. And we'll assume, again, that, mostly to help ourselves here, that the range of values each measurement can produce is discrete. In fact, I'm saying 1 up to k here, mostly we're going to just look at binary processes. And one of the reasons we're doing this is I want to give you a picture, a visual understanding of what the space of sequences looks like. And it helps to do that in a discrete alphabet case, discrete time, discrete alphabet setting. Okay, just like before with probability theory, capital letters mean random variable. Lowercase means a realization. So if this was a binary random variable, a realization would be heads or tails, 0 or 1. So we'll talk about by infinite chains of random variables. You should imagine infinite past, infinite future. And then we have words, which are realizations, actual 0, 1, or head-tail sequences. So we have this by infinite chain, and I'll denote that with the random variable symbol and this double arrow. And typically think of this, we stop at some moment in time, and there's some past left arrow that's going to lead to some future right arrow. So just to lay it out here, typically when I say time t, we're looking at the past, the random variables just go up to the random variable at time t minus 1, just a convention. The future variable, as forward arrow at t, includes the random variable at time t and goes forward. So we take the bi-infinite sequence and break it into the two semi-infinite sequences, a past and a future. More practically, we'll also be looking at blocks of over some period of time with these random variables. So here's the full notation, a block of length L starting at time t. This is useful, for example, when I talk about if you actually had finite data, right? We're not going to have semi-infinite sequences of random variables or data for that matter. And then it's a little bit of vocabulary. If I'm thinking about a particular L block set of random variables, its realization, I'll refer to a word. The word heads, heads, tails, heads. So just a note again. Same notation except lowercase. Okay, so the thing we're going to study, the object of our interest, is what we're going to call a process. Now, the most general definition, in the sense I was just talking about the raw sequence of behaviors, but they also occur with various probabilities. So a process is going to be this ungodly object. So with nothing else said, with minimal set of assumptions, we have this bi-infinite chain of random variables, infinite past, infinite future, and for each one of those, we assign a probability to it, which is a perfectly unworkable representation of a process. And a lot of the goal we're pursuing is how we can come up with more compact descriptions of the process. So we'll talk about that today. Again, sort of practically, we can also talk about sequence, typically I'll say word distributions, and that is the set of probability distributions over the L blocks. So this is a very big set here, right? And this is essentially an alternative way of specifying a process. I specify the probability of the length 1 words, the length 2 words, the length 3 words, the length 4 words, and so on, off to infinity. So that's another way to specify a process. Also, unwieldy. There you have it. So think of this as the raw data. A lot of times I'll just give you a process. I'll specify it somehow, typically maybe in words, like a process that cannot generate consecutive zeros. And then you can ask what kind of probabilities we can assign to the words there. And then try to see what possible models we can come up with for something like that. Okay, so we have these words of length L. We're going to say that a word is allowed or admissible. One finds either word used when the word has positive probability, or inadmissible if it has 0 probability. The example I just gave, the process that cannot generate 2 zeros in a row would have a length 2 word, 0, 0, that has 0 probability. All the other length 2 words are admissible in that case. Now these distributions that we can put on top of words have certain consistency requirements. Namely that the longer a word, typically the probability goes down. The probability of flipping 2 heads in a row for a fair coin is 1/4. I guess what's the probability of seeing 3 heads in a row? That's 1/8. Right, so probabilities go down. In fact, more directly, if I have the distribution over length L words, I can marginalize over the last symbol and get the probability of seeing the shorter word, or I can marginalize over the first symbol in the length L sequence and get that. Okay, so these are constraints on what these probability amplitudes are when I assign them to words. In addition, when I have a process, we say that if I've seen a given word, say 10 tosses of fair coin, I've seen every subsequence. It's kind of a trivial thing, but mathematically, we say it's subword closed. That if I've seen some longer sequence, I've also seen every other sequence inside of it. In particular, those words are admissible. The words of length 1 and the length 10 sequence, the words of length 2, and so on. It's kind of obvious. And the reason we emphasize that is in computer science, there's a different notion of what are allowed words. You can have a word 10 that, say 101, that's an allowed or accepted sequence in formal language theory. However, the word 10 is not. So this is more of a physics setup where if I've seen a sequence, that means necessarily I saw all the measurements up to that sequence. So our processes are going to be subword closed. The probability distributions will have these consistency conditions on them and so on. Okay, well, so what kinds of stochastic processes are there? So what I want to do now is talk about just the processes. What behaviors or sequences occur and their probabilities. I'll give you a number of examples that we're going to keep coming back to, probably at some point. Too often, they become too familiar. And then I'm going to shift, and this is just a little bit of a conceptual change to shifting from behaviors and their probabilities, the process, to models of processes. And it's very often we think about processes in terms of their models, but actually it's two separate concepts. And we need to make that distinction because processes for us are going to be the theoretical stand-in for making observations. And we want to learn models, so they're not the same thing. If you're confronted with data, you don't necessarily have a model of it yet, and you'd like to learn that from the data. Or mathematically, I'll give you a process, and what is a good, compact, verbose representation of it? So we want to be able to ask those questions. So I don't want to confuse the notion of process and model, at least not too soon. Soon we'll move back and forth very quickly. Okay, so first kind of process that's often studied are stationary processes. And that's a pretty simple idea, namely that the word distribution, these probability amplitudes, don't depend on the time origin. So, and there are different settings in which you would want to do that. You don't want to worry about the process starting condition, or you imagine the experiment in the lab has been running for a long time, you went out for coffee, you came back and it's still running. You know, all the equipment is stopped drifting around, everything's heated up, and the probability of seeing 1, 0 at the beginning of the experiment is the same as the probability of seeing it an hour later. Okay? So, or we can imagine that we're doing many experiments and we assume that, again, if we see 1, 0 in the first trial, that probability we measure will be the same as some later trial. But again, it just means that this distribution is essentially independent of time. So very often I'll just take t and assume it's 0. And this would be true for every t. That's equal to probability for the block at time 0. We don't have to assume this, but it's very handy. It will kind of dominate the kinds of processes we're looking at. Again, it simplifies things. A lot of the ideas we'll talk about become very interesting when we have non-stationary processes, or even the practical situation is if I have some data, you know, are the probabilities kind of drifting around because of experimental conditions or external perturbations I haven't taken into account or not? How do you test for stationarity? So all interesting questions. We're just going to assume it for now and see what the consequences are. One notational consequence, I'm pretty much just going to drop time indices. If I'm talking about, you know, the length 3 word at hour 13, it doesn't matter because it could be the same length 3 word at the beginning of the experiment or 4 hours later. So I'll just drop t, that's convenient. I'll just be referring to length L blocks, length L words. It doesn't really matter when they occur. Okay, simple kind of stochastic process, stationary stochastic process is the uniform process. So, easy to say in words, equal length sequences occur with the same probability. So, it's simple, I'll just denote that. If I want to write down the word distributions for it, I can do that very directly. The probability of words of length L is simply 1 over the alphabet size to the L. If I had a fair coin, heads and tails, equal probability, I can write out exactly what the word distribution is for all lengths. It's just 1 over 2 to the L. I'm looking at length 4 words in the fair coin. There are 16 of them, 2 to the 16, and they each occur with probability, 2 to the 4, there's 16 of them. They each occur with probably 1/16. Okay, so that's compact representation there. Actually quite helpful. It's a good reference point. Sort of probably the most uninteresting process we'll look at, but there it is. Whenever we introduce new properties, the first thing we do is calculate it for this simple case. Now, a little more sophisticated class of process would be the independent identically distributed class. So what that means here is, okay, so independent, what's that mean? So I have this giant joint distribution over past and future, by infinite past and future. That means that it factors into this product of the distribution of individual symbols at different times. And that these individual random variable distributions are the same at any time. So, independent, and then identically distributed. And you will see this all over the place. Again, these are assumptions that are helpful because they give us simplifications we can work with when we have questions. Bias coin, we will come back and talk about this repeatedly. And you'll see there's some actually really puzzling things about this. But at first blush, you just imagine that the probability of heads is probably p, probability of tails is 1 minus p. We can even write out in closed form exactly what the set of all the word distributions are. Just p to the n times 1 minus p to the l minus n, where n is the number of heads. Should be very familiar. So, nice closed form representation of the process for all L. Rarely do we get to do this, but there it is. Yeah?
So, an IID process is stationary, right?
Yes, right. Right. Mm-hmm. Right. Right. It should be a little exercise. It's using some of the definitions, but yes, it's stationary. Another kind of process is what we call R block process. And what we mean here is this, basically the process just writes out blocks of length R. Okay, so say it more formally, we take our giant joint distribution over the bi-infinite random variables, and we have these blocks that are independent of each other, just like before. So it's one way to generalize an IID process to blocks. We're really just making a distinction here between an alphabet and then these blocks. So a 2-block process that can't generate consecutive zeros would be this one, so binary alphabet. Probably 0, 0 must be 0, and I just assign probabilities to other words, just 1, 0, and 1, 1 have probability 1. Call this the noisy period 2 process. We'll come back to that. Right, so this process, as it's laying down these 2 blocks, will never generate consecutive zeros with this setting of the probabilities. That's why this one is 0, 2. Because if I wrote this one down and followed it, then I'd have 2 zeros following each other. So I set that one to 0. And again, what this means is if I had this length 6 sequence, the probability of this one breaks down into this product over length 2 blocks. Now, probably one very large class you've heard of are the Markov processes. And what this means in the first case is this joint distribution factors into this telescoping product of one-step conditional distributions. Right, so it's a slight generalization. What it means is that the next measurement depends on the previous one. Measurement at t plus 1 depends on t, that at t plus 2 depends on t plus 1, and so on. Just one-step dependence. You can see how it's a generalization from the IID process because there was no previous dependence. So it's a slightly more general type of thing. Here's another process that cannot generate 2 zeros in a row. 2 zeros in a row. It's called the golden mean process. This would be a good friend of ours after several lectures. Again, binary alphabet. And then what I do to specify this are this sequence of 4 conditional probability distributions. Well, I can't generate 2 zeros in a row, so probably seeing a 0, if I saw a 0 before, is 0. And then I've assigned these probabilities, assuming the consistency conditions and so on. I have some choice in these probabilities, but they also have to satisfy those consistency conditions when you produce the word distributions. So this is a slightly different process than the previous one. They actually are similar up to length 4. The golden mean process admits this sequence, which the previous one didn't. Okay, now, start kind of merging these things together here, generalizing the Markov process to having a dependence over the R previous variables. So what that means is that we think of that giant joint distribution over infinite past and future as broken into a series, a product of conditional distributions, just like for the one step one we just did, except that the dependence now just goes R steps back. In general, for a general process that could depend on the entire infinite past, but we're just going to just go R steps back.
So, would this be equivalent to a Markov process with different symbols? Or is that...
Yes. There are various ways of converting these back and forth, and we'll come to that. Right now, we're talking about processes. In a sense, when we start thinking about different ways of encoding them, we're getting closer to models. So we'll deal with that as soon as I shift from this kind of very raw description of a process in terms of probabilities over words or conditional probabilities over words. After a while, it gets a little tedious, and we just have to introduce some models. It simplifies the vocabulary. But it's sort of a related question is, how are these different classes of process related? So here's just a simple little demonstration that an order R Markov process is more general than an R block process, right? So we, in some sense, both R block processes and order R Markov chains, they're telling us something about relevant timescales in a process, namely R time steps. Dependencies exist over R time steps. So if we just factor this length 4 word, we get this just using usual probability identities. Yeah.
When you say order R, is it always understood to be an order R Markov?
I will probably mess up sometimes, but yes, that's generally what I mean. Yes, yes. Yeah. And then going back to the definition of conditional distributions, I just rewrite the two middle ones here as the ratio of a joint to a marginals. Okay. And then rearrange things. And then you notice that I can end up with a two-block process where the blocks are independent if this and this, namely this ratio, is equal to 1. So if I assume this, namely that the joint distribution between the second and third random variable basically factors into its product, namely that those two random variables were independent, they're 1 here, then I'm sort of breaking the dependence here. So the order R Markov process, the dependencies are, you think of them as like a sliding window, whereas the blocks are just fixing. At the end of the block, there's no more statistical dependence, end. So the order R Markov processes are more general. There are a wider range of processes that you can represent. It's an order R Markov process than with block processes. Okay, so again, sort of like with our dynamic systems, that was us looking in the box and seeing the behaviors. Now I'm going to interpolate a measuring instrument here, and we'll talk about hidden Markov processes, where we don't get a direct, we don't get to know what the sort of internal state or symbol is that's given to us by a measuring instrument. So what I'm going to assume in this case is that we're going to have an order R Markov process, okay, that just length R temporal dependence, and then this is going to be observed through some instrument, which I denote F here. There's some mapping from the bi-infinite hidden sequence to an observed sequence Y. There'll be a different alphabet now. We have to call that B. We have this sort of measurement random variables, which itself is this bi-infinite chain. The observation process, how we actually go from the S variable, internal variables, to the observed ones, is given by a conditional distribution. It's one way of thinking about what this F could be. In fact, in this case, this f could be some stochastic function. It could add noise itself, not just be a direct mapping. And then we have the situation of being an observer. Actually, all I have would be this process, this observed process, otherwise. And of course, practically working with block distributions over the observed sequences. So this is typically what we have to work with when we're doing experiments. And most of the questions, interesting questions we'll be dealing with will be how much and what can we extract from Y that tells us about S, what S is, what these internal dependencies are. How much in this observation process is thrown away, and how much is added, distorted. So I'll show you some examples of this today. So here's another example prototype process that we'll work with a lot. It's called the even process. The names of these processes will become clear as we begin to analyze them a little more. The previous one I called golden mean, no consecutive zero. This is called the even process. So this might become a little bit clear here. Okay, so the internal process is going to be the golden mean process, right? So let's take a binary alphabet. So this is generating all binary sequences except no consecutive zeros. If I see a 1, I have to say something else to give a complete specification. If I see a 1, then I see 0, 1 on the next time step with fair probability, turns out. Now, the observation process is going to have the alphabet little a, little b, okay? And it's going to be a function of the output that I see, the symbol, AB symbol that I see, depends on the current internal binary variable and the previous one. So it's going to map from, so this F has a little bit of memory. It's going to map from the current and past variable, these two blocks, to a single symbol. And so here's the rule. If that internal 2 block was a 1, 1, I output an A. And if it was B, and if it was 0, 1 or 1, 0, then I output a B. And since it's the golden mean process, I don't have to write down a rule for 0, 0, because that doesn't occur. That definition doesn't occur. Okay, so here's an example of this, how this F is working. So here's my sort of chain of a realization for the internal golden mean process. Notice all the zeros occur in isolation, so no consecutive zeros. And then I just go through and apply this rule. If I saw 1, 1, I output an A, 1, 0, B, 0, 1, B, 1, 1, A, 1, 1, A, and so on. Simple enough. So that seems nice and innocent. Did you see why it's called the even process? 2 B's, 2 B's, 4 B's, 2 B's. There's more to say about this. Okay, so that's an example. And somehow this simple local measurement function maybe has done something interesting. The question is what is interesting about this, so we'll get to that. Okay, so that's just some example processes. We're just talking about words and their probabilities. And like I said, this gets a little bit tedious after a while. In fact, as I was trying to explain things, I was trying not to use the word model, or in particular the word state. But this is really a natural way to think about processes, state-based models. So what I want to do here is sort of roll back and kind of work our way up through classes of representation of processes in terms of models. Okay. So the simplest is called the Markov chain. So we have a Markov process, and we're going to represent that with a model called the Markov chain. The way we think about Markov chains is that they have some internal states. Well, these states are simply going to be the measurement alphabet, the observed alphabet there. And we'll have some internal state process over this. Okay. By a chain of random variables, just denote that V. And then now we have a dynamic that maps from one state to the next. And since it's a Markov process, this is going to be given by a one-step conditional distribution. The probability of the next state depends on the previous state you were in. Okay. So we'll think of that as a matrix that gives us transition probabilities going from state to state to state. The transition matrix, every row sums to 1. So these are called stochastic matrices. Every row sums to 1. And what that means is you always make a transition. Doesn't matter which one. They might occur with their problems, but you always make a transition. And just like you were saying before, we can, if we wanted to recast an R block process, what we do as a Markov chain, what we can do is we'll just assume the blocks now are the states of the Markov chain. We just enrich our alphabet to be alphabet size to the R for the blocks. So now blocks become states, and they're these unitary things, and now we just think of them as states in this much larger transition matrix. Okay, so map back and forth. Probably depends on what your questions are in a given application if you want to do one or the other. Now there's some more things we can say. We have these states, and at each moment in time we can ask what's the probability of being in one of the k states. So it's a state distribution. We'll just think of that as a vector of numbers. And we have this transition matrix, so we can use that to evolve a probability distribution forward. Should be certain echoes of what we were doing before, except this is much easier to think about. So just to point out here, mathematically, we have a choice. The way we're going to set this up, the way we're going to normalize the transition matrices, we multiply from the left. We take the state distribution, multiply it from the left against the transition matrix. So state probabilities goes into the transition matrix, and we get the probability of each one of the states at the next time. We could have done right multiplication, but just out of habit, we have a choice. It's left multiplication. Given that this is the one-step evolution of the state probability distribution, we can just iterate this again and again to start from some initial distribution to get one n steps later, and that obviously just by induction is just do that in a sense one step if I had the transition matrix to the nth power. So again, we have a state sequence. We might want to know if I have a particular length L state sequence, what's its probability, and that just is, again, because it's Markov process, just given by this telescoping chain of conditional transition probabilities pretended with the probability of which state we start in. So that's just factoring this joint distribution out this way and assuming the one-step Markov, order 1 Markov property. This is typically what they look like. If we had 3 internal states, we'd have a 3x3 matrix giving the transition probabilities from B to B or C to B and so on. They're all normalized. The T being stochastic means these equalities here, and then graphically, and we'll use a lot of graphical representations of these state-based models. We have 3 states here, the circles. We have arrows connecting them, and then the arrows are labeled with transition probabilities. So you can either think of it this way, or you can think of it this way. You'll see after a while, this way is deeply uninformative, even though that's how we represent it in code and calculate things. We'll get comfortable with these label-directed graph representations of Markov chains. And you can sometimes pull out properties pretty quickly just by visual inspection. And this is going to help us be more explicit about when we talk about how processes are structured. In the general case, there are different kinds of states for a Markov chain, and we'll need to distinguish these things. So here's one of these label-directed, I should say, yeah, label-directed graphs. We've got 6 states here. There's a certain kind of architecture to this that we'll end up being very interested in. There are states like A, B, and C, such that if you rattle around in them for a while, you'll eventually transition out of and never return. Those are called transient states. So here, if I had transition probabilities, there'll be some probability that I'll eventually transition to B. I'm never going back to A, so it's relatively transient. I might have this kind of A, BC, BC, BC thing, but eventually, if there's some positive probability, I'll leak out here down to the set of D, E, and F, and never go back to A, B, and C. So those are called transient states, and then there can be a set of states called the recurrent states that you rattle around in for a long period of time. I could even make this more elaborate, have several recurrent components, and so on. So that's our first kind of graphical hint that the structure in the transition matrix can be useful to us. We can also sometimes specify a start state. I'm going to start in state A with probability 1. I could have several start states and say I'm going to start in state A and state H with probability 50-50. Another sort of architectural observation is that you can have subsets of states that are strongly connected. That means you can get within a strongly connected set, every state can get to every other state. So B can't get to C, but A can get to itself. B and C can get to each other, so that's a strongly connected component. And then the way I've drawn the recurrent set, these are all strongly connected. D, E, and F can all get to each other eventually. So the graphical representation of these models is helpful when we want to start talking about how they're structured. There's a little more we can do. You might be interested in, as the model process is operating for a long time, in what state distribution we have at long times or asymptotically. So that's the limit of pi. And as we sort of noted before, if I specify an initial distribution over the states, I can push that forward with t to the n. So this is really, the asymptotic state distribution is really just a property of powers of the transition matrix. In fact, the way you calculate it is you look at this, we're looking for a vector pi, this vector over state probability such that when it gets multiplied into t, it comes back to itself. Right? It's a fixed point distribution like we were talking about before we're talking about systems. So this, in linear algebra language, we're looking for an eigenvector and it's associated with an eigenvalue of 1. This is called the principal eigenvalue. It's 1 for a stochastic matrix like these transition matrices. And then we look at a vector that will satisfy that. This eigenvalue equation doesn't specify the asymptotic state probabilities completely, but we assume normalization. So it's an additional condition of a family of distributions that can satisfy this. We pick the one that is normalized. And now, this one maybe small question we could ask. If we've been looking at a process for a long period of time, and we come in and we observe a particular sequence, state sequence, what's its probability? Well, now we can assume that we're starting in the first sequence. Before it was arbitrary, it's just P of V0. Now we can assume, it's been running for a long time, that we're in state V0 with this asymptotic state probability. And then lets us calculate sort of long-term probability of seeing a particular sequence for a Markov chain. So some examples. Fair coin again. So I can either write down, I have sort of two states, heads and tails. I have a 2x2 matrix. If it's fair, then the transition from heads back to itself or to tails is equal probability. Same thing going from tails back to heads or tails. I can write out the label-directed graph. So I have two states, heads and tails, and then the edges. All edges are there, and they all have the same probability. Go calculate this eigenvector normalizing probability. It's 50-50. No surprise. I'm going to degenerate here. Right, and we conclude that probably heads and tails is a half. You could also imagine that we had a much larger alphabet, and you can sort of now picture what that looks like. Right? It has as many states as there are symbols in the alphabet, and then as many transitions as there are symbols in the alphabet. Right, all states can get to all states. Okay, so now what I want to do is to shift over, using the examples, the processes and the models I've introduced, to start talking about what the space of sequences looks like for these different cases. Okay, so what we're going to do is start with a fair coin. And again, we can write down exactly what the word distributions should be for any length. So that's no mystery here. And what I'm going to do is and we kind of talked about this a little bit when I introduced cellular autonomy. So in order, we want to look at the space of all sequences generated by the fair coin. So what I'm going to do is take each word of length 1, of length 2, of length 3, and stick a binary point in front of it, and then interpret it as a number on the unit interval. Okay? So in some sense, I'm metrizing. Every word here is going to be, the bits will be weighted by some power of 1/2. Right? So if I have 1, 1, then I have the first thing would be weighted by half, the next digit would be weighted by a quarter, and so on. And then when I do that, so what I'm going to do here, this is a mosaic of word distributions, the length 1 words, length 2 words, all the way up to length 9 words. I did not write down this boring constant function. What I did here is actually just generate, kind of flip coins, and calculate empirically. So there's some noise here which has to do with finite sample noise. Okay, so here, length equal 1. I should say, the vertical axis is again log base 2 of the probability. So words of length 1, well, we just have heads and tails, and they occur with equal probability. So at least empirically, that sample had almost exactly the same number of heads and tails. Now what I've done here is there are only 2 words, so you should think of this like a histogram. On the unit interval, I've drawn a probability of 0 as this bar here, and probability of 1 as this bar here. Okay. Now when I go to length 2, there are 4 words, right? 0, 0, 1, 0, 0, 1, and 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. I now have 4 bins. I'm putting the probability above each one of those bins, but it's also uniform here, other than these little kind of statistical estimation errors. Length 3, we have 8 words going from 3 zeros up to 3 ones, and I'm laying them across in sort of increasing order, sometimes called lexicographic order, or just numerical order if they're these binary fractions. And so, like 4, 16 words, like 5, 32, 64 words, until I get like 9, 512 words. So you can see, it's not really the point of these slides, but you do see that the statistical variations are increasing because I'm trying to estimate the probability of 512 events here, and I have fewer counts of those than just kind of heads and tails in the same sequence. So my estimate of the probability, which should be exactly flat, is modulated. Again, if I took enough samples, it would converge. In fact, the fluctuations here go down as 1 over the data length, 1 over the square root of the data length. Okay, so that's just mostly to introduce this mosaic word distribution to get some sense. Nothing surprising here. Bias coin. Okay, so you can write down the transition matrix, probability of heads going to itself, probability of heads going to tails, and so on, or this graphical model, which are much easier to read. You can go calculate this asymptotic invariant distribution, pi, and it's p and 1 minus p. Again, no surprise. Probability of heads is p, tails 1 minus p. Bias coin is nice because it also gives us a picture of what all of these IID processes look like, especially when we think in terms of these graphical models here. Markov chain has as many states as there are symbols, and then the transitions leave each state and go to all states, right? So it's sort of like the generalization to the uniform process over more symbols. One interesting thing is that you can say that the previous model doesn't show us that the transitions entering state I have the same probability as state. So notice, so the probability of heads is p, and notice that the transition probabilities coming into state H are p also. So very highly constrained. These IID processes are very, very highly constrained. Or easy to read properties off of them, if you will. Okay, now for something fun with the word distribution mosaic. Again, so bias coin, and I can write out in closed form what the word distribution is for any length. Okay, so here, right, it's just probability of heads to the number of heads in the sequence, times probability of tails to L minus number of heads in the sequence. Okay, so what I'm showing you here is a simulation run, again, where I have probability of heads is 60%, probability of tails is 40%. And so, of course, when I look here at length 1 words, that's just probably heads and tails, we see a difference. Okay. We go down to length 2, we have 4 sequences again. So tails, tails, heads, 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 tails, and heads, heads, or say in terms of zeros and ones. And we see there are these steps now appearing. Of course, the most probable sequence would be 2 heads in a row, 60% times 60%. These 2 middle sequences, tails, heads, and heads, tails, well, it doesn't matter which way I multiply the probabilities. 40% times 60%, or 60% times 40%. you get the same probability amplitude. And then, of course, the least probable sequence is tails, tails. So now I'd like to just say, and so on, right? We go now to length 3 sequences, 3 tails in a row, 3 heads in a row, still the most probable, still the least probable. But now we're starting to get some funny structure in there. Now just let your eye kind of sweep over to like 4, like 5, like 6. You start to see it's a really complicated set of probability amplitudes. All the words occur, right? They're all admissible. They all have positive probability. What we're seeing is that the distribution of the words is getting really complicated until finally we'll actually get down to the statistical fluctuation. But you see it gets more and more refined. This is just a biased coin. And here we are, we're just trying to get some sense, in particular in the limit of infinite length sequence. What's the distribution? That was easy to do in the case of the fair coin because it was just flat. So you kind of understood what the infinite sequence probability space looked like. Just with the biased coin, suddenly there's something completely non-trivial occurring. We're getting this almost fractal, as it turns out, fractal distribution of probability amplitudes, and it gets more and more refined as we go to infinite length sequences. Yeah?
So if you make the x-axis like a breakpoint, do you still see that, or does it become more flat?
It becomes, yeah, you can, right. In some sense, the self-similar structure here depends on the particular way I've metrized the space of sequences. I could sort them from most probable to least probable, and then there are other sort of conclusions you can sort of draw for the bias coin about the distribution of amplitudes, probability amplitudes. But this is, despite that, this is still a nice indication of how, even though this process is very simple, just a bias coin, there is this diversity, independent of how I plot, there is this diversity suddenly created in the probability amplitudes. And there becomes this question, how do we start describing it? This is one of the things we're going to have to deal with. Not only which behaviors occur and don't occur, but also complications in the distribution of probability amplitudes.
It seems like there's like a definite structure in the 6 and 7 one, but then in the 9 one it starts to get washed out. Is that just a function of noise?
Yeah, I should have taken a longer sample length, and that would, yeah. Yeah, in fact, the self-similar, you can kind of imagine, take this half, expand it out, it's exactly that half, but the right rescale. So, however you plot it, whatever your choice of metrizing is, it's going to have that self-similarity. Well, the fair coin had it too, but it was just a flat distribution going to a flat distribution. This is interesting because of this real diversity. The fact that there are an infinite number of different probability amplitudes when L goes to infinity. So how are you going to deal with it? Typically the way you deal with it is you say, oh, that these actual probability amplitudes are randomly distributed and they have a Gaussian distribution. And there's a mean value and a distribution about that. Okay, so this is just kind of a first hint that things get complicated. When we're trying to describe behaviors, sequences, we'd like to understand what the structure of that space is, and this is the first hint that it's complicated, at least in terms of probability amplitudes. Okay, well, maybe something simpler. Another example, periodic process. So ABC states the probability 1, I go A, B to C to A, and so on. And then we just have T is now just a permutation matrix. There's just, each row just has a single transition probability. The only curious thing here, and this is the reason I pointed out, is that if you wanted to calculate pi using that eigenvalue equation, right, left multiplying, looking to see if it comes back to itself, maybe it's best to kind of explain this on this graph. I can put any initial distribution down on here. Under one step, it will come back to itself. I can go a quarter, quarter and a half, and after 3 steps, it comes back to itself. So who's to say it's invariant? So you actually have to be careful in this trivial, with behavior to be a trivial case, periodic. You actually have to be careful how you calculate this pi from the eigenvalue equation. I can put any distribution here, and it'll be invariant. So we'll come back and solve this little problem in a different way later on. There's a natural way that asks about how distributions relax down onto the asymptotic distribution. So sequence distribution here is really simple.
Is that just looking for higher period orbits, right? Because this is invariant distribution under a single.
Under one step, right? Exactly.
One step,
yes.
Right? So you would look for invariant distributions under 2 steps or 3 steps.
Yes. Well, okay, so, right. So the point I'm making is let's think about doing it 3 steps. Every initial distribution is invariant under 3 steps. Right? Point 1, point 1, point 8. 1 over pi, 1 over pi, goes on. You know, it's everything under 3 steps.
Not if you look at the eigenvalues of TQ.
Yeah, it turns out that it's so degenerate that the standard ways of calculating them don't work. Yeah. So most of the way, when you have nice, what's called mixing properties, you actually have these initial distribution being spread out, in other words, kind of a discrete analog of chaos. Then the standard eigenvalue analysis techniques looking for the eigenvector work fine. But in these periodic cases, or if you have a little bit of noise, a little bit of branching in this, and an overall periodic component. Imagine you had 3 biased coins hopping between each other periodically. Same issue comes up, so it causes, yeah. But we're actually going to like that sort of thing. The other sort of obvious exercise here is just you can show that, in terms of the state distribution sequence over states, basically, for long words, there are only 3 words that occur of basically any length, and they all occur with probability 1/3. Right. So the states themselves are probably 1/3. Probably seeing pairs is also 1/3. Length 3 words also have probably length 4. There are only 3 length 4 words, 3 length 5 words, and they all have probably 1/3. So, okay, simple enough. So, a model of this golden mean process, right? So before it was just defined as don't generate consecutive zeros. So here is how we represent this as a state-based model. The states now are going to be these length 2 words. 0, 0 doesn't occur because that's can't be produced by the process. You actually have to, it takes a little while to sort of work out the transition matrix here. How 1, 0 transitions, 1, 0 transitions to 1, 1, and so on. It takes a while. I've drawn that out explicitly. You'll notice that there is a restriction. I can't go from 1, 0 to 0, 1 because that would put 2 zeros next to each other. So there's an edge down here that's missing from the complete all transitions 3-state label directed graph I gave you before. So there's an edge here. I can go the other way, but not back this way. And that affects all the other probabilities. These blocks, just by doing the calculations I mentioned, you can show that they occur with equal probability. Here's another model of the golden mean process, no consecutive zeros, that uses only 2 states. So here, what I'm going to do is just take the alphabet, now just the binary alphabet, and take those as my states. And what this model is showing you is that if I see a 0, I must see a 1. If I've seen a 1, I can see a 1 or a 0 with fair probability. But if I see a 0, I must see a 1. So it's a perfectly valid, obviously easier to interpret than the previous one. Simpler 2x2 matrix. And now we have these different states, right? So we have to go calculate this so-called left eigenvector normalizing probability and find out that the sequence that's produced by the golden mean process, 1s occur with probability 2/3 and 0s occur with probability 1/3. Interesting conclusion. This is now an order 1 Markov chain, and it's sort of a minimal order, minimal size. We'll talk about smallest models. That's going to be an important property later on as we start building models. First observation is that I specified the process, and I gave you 2 models. This gets back to the main point I was trying to start out with. We don't want to confuse models with processes. Processes are what occurred. And we have different representations. Actually, in the language of the field, we call these different presentations. So the 2 different models, this 2-state model and the 3-state model, are 2 different presentations of the golden mean process. Sometimes that's a good thing to have different models. Sometimes certain properties are easier to calculate or just easier to work with. Trying to find transformations from one kind of model class to another could be very helpful, especially with simplifies calculations. Oops, sorry. So the golden mean is also a nice example of combination of things. Namely, we already saw with the biased coin there, as we go to long sequences, the distributions of the words get really complicated and have that self-similar structure. Now we also have a restriction. Certain sequences don't occur, those with 2 zeros in a row. Okay, so let's kind of talk through the word distribution mosaic and see if we can see those things. Well, okay, length 1, well, zeros and ones do occur, and I just told you with that second model, ones occur with probably 2/3, zeros occur with probably 1/3. Now we go to length 2, and what happens? Well, the first thing is that 0, 0 doesn't occur. So we see our first restriction here. And just coincidentally, the 3 other words, 0, 1, 1, 0, 1, 1 occur with probably 1/3. Now we go to length 3. What's happened here? Well, 3 zeros in a row, 2 zeros and a 1, and 1 and 2 zeros all have 2 zeros in them, therefore they're forbidden. So due to this no consecutive zeros restriction, there's a consequence of longer words. It cleaves out the admissible sequences. In addition, of course, there's some interesting things going on with probability amplitudes too. Length 4, well, I won't go through it in detail here, but all of these gaps here are words that at least contain 2 zeros in a row. Length 5, length 6, and so on. So now, kind of letting your eyes sweep over this, you kind of imagine this single restriction causes a cascade of restrictions and precludes longer words from occurring. In fact, the way they occur, so now we're excluding things in the support of the word distribution, the sequences. The way they occur is self-similar. You can kind of imagine, let's see, not too obvious. Well, roughly speaking, this guy looks like this guy looks like that guy. It's a little more complicated to draw by eye what this looks like. And it keeps getting more and more refined. And in fact, the gaps sort of start taking up more and more of the space. This might remind you just a little bit, visually of the dissipated Baker's map. And there's even a notion of fractal dimension. You could calculate fractal dimension. But we're going to come back and reintroduce that idea with information theory. Turns out it's related to something called the entropy related process. How many sequences occur as L goes to infinity. Overall, what's going on? There are 2 things here, right? First, we already talked about with the biased coin, there's sort of complicated things happening with the probability amplitudes, that structure we'd like to capture. And now, the support of the distribution. It's kind of complicated. Every time there's a restriction, there's a cascade, there's a set, called the Cantor set, that's included at infinite length, the self-similar set. So there are really 2 lessons here. We can have structure in the behaviors, namely the support of the distribution, which words do and do not occur, and also in the set of probability amplitudes. And there's a very practical question. If you were trying to build a model, and you see or don't see sequences, you're making some estimate of the probabilities, is what you're seeing due to structure in the distribution, no probability events, or you don't actually see something. So anytime we're doing estimation, we're sort of mixing these 2 things. And I tried to draw with the word distribution mosaics very clearly. I mean, we know what the processes are, so we know what's exactly going on. We can see how these things can interact. And these structures do, 2 different kinds of structure do play, they couple together whenever we're doing some kind of statistical estimation. Okay, so these were just Markov chain models of Markov processes. The real thing we're interested in is taking into account measurement distortion. So I want to talk about hidden Markov models of processes generally. So like the hidden process we talked about before, there'll be some internal states, but now I'm going to think of this as some kind of Markov chain. So it actually has states, not just raw sequences of symbols. So internal states in some alphabet, and then there's an internal state process given by a transition matrix. So that's just a Markov chain. Now we have the observation process. So the way we're going to represent this is we're now, in a sense, take the state-to-state distribution matrix and kind of split it into those transitions that emit this or that symbol, that generate an A or a B, say. So instead of these sort of one-step state-to-state conditional distributions, given that I'm starting in state V, there's going to be some distribution over what state I go to and then what symbol I'm going to emit or see. And if we do that, then we can recover the internal state transitions by basically summing out the observed symbol. So we easily recover this. And just like the internal Markov chain matrix is a stochastic matrix, all rows sum to 1, there's also a normalization condition for these sort of measurement symbol labeled transition matrices, the TSIJs. Before, we had an internal state distribution. We knew how to calculate that using powers of the matrix or doing the eigenvalue analysis to get the asymptotic state distribution. Fine. The state sequences, we can now calculate exactly their asymptotic probability because we know the asymptotic state visitation probability, so we can write out those telescopic products exactly. But now we've got observed sequences on top of this. Okay, so now we're seeing sequences of words over a different alphabet through some function. And a simple question that we ask in every case is, what's the probability of a sequence? Well, before, when we were just looking at Markov chains or looking at the internal Markov chain, we got to write out this explicit telescoping chain because we got to see the state values. Okay. Now, if I see, if this was, say, a binary alphabet, and now I'm looking at strings that are being produced over A's and B's, I might have a particular A-B sequence, B-A-B-B-A. And what I have to do now, notice the sum here, I have to calculate out, starting in all possible states, sequences of state transitions that would produce that observed sequence. In other words, for a given observed sequence, there could be many internal state sequences that could produce it. I'll give you some examples here, but this is the main difference here. So now, suddenly, up here, we had this sort of one-to-one mapping, if you will, mostly because we get to look at the states. We no longer have that between the internal sequences and the observed sequences. And this is it's another challenge for trying to figure out what's going on internally. So multiple state sequences can produce the same observed sequence. There's a degeneracy there, and the question is, if I just have observed data, how can I ever figure out what the possible multiplicity of internal states is? And surprisingly, there's going to be a positive answer to that. But it's going to take a while to get there. First, let me just kind of finish introducing the hidden Markov chain or model class. Again, the internal thing, just like before. Right? We have 3 internal states. All possible transition probabilities are labeled here. Now we have an observed, say, binary alphabet. And we now label the transitions with the sequence that gets observed and the state-to-state transition probability. We have those pairs there. And now we kind of separated out T into 2 different matrices, T0 and T1, with these refined transition probabilities that also give us the probability of seeing the symbol. Yeah?
Is it always the fact that you encode what you observe on a transition, or is it what you observe in a state?
Right. So actually, if you go to a lot of the literature and textbooks, what you're going to see for hidden Markov models, where they put the observed symbol on a state. So I come into state A and I emit a 0 or 1 with, say, some bias coin probability, something like that. That's overwhelmingly the model that's used. So it's a little bit of a kind of a heads up or even telling you part of the punchline. It's extremely important for us when we talk about building models and giving this positive answer I just referred to disambiguate states from observations. Right? So the contrast I've been trying to draw here is when we had just a Markov chain and I saw ABC, in a sense, I had my head inside the box. But now when that process is hidden and it's generating zeros and ones, I don't want to confuse the zeros and ones with states. And so what I do is we put the symbols on the edges and not with the states. We're going to come back to this property again and again and again, but very helpful eventually. Even has very quantitative impact when we use information theory to measure how much uncertainty there is in sequences. We want to disambiguate that from the amount of state information the process is using. So it's sometimes I pass through this and no one notices, but and there's maybe a little bit of difference in trying. If you go read another standard book on Markov chains, hidden Markov models, it's like what's the difference here? They're all okay. Both edge-labeled and state-labeled hidden Markov models describe the same class of processes, and there's a way to interconvert between them. So there's no loss of generality here, but in fact, there's a lot of clarity we get from doing this, and some kind of new ideas about state complexity of processes. In fact, here's, in a sense, kind of the first kind of consequence of this choice. So, as I said, there are different types of hidden Markov model. State labeled, we're looking at edge labeled, and we can think of edges, starting state, ending state, and the symbol emitted as an event, as an associated probability. Now, there's a class of these edge-labeled hidden Markov models that we're very interested in. And these are called unifilar hidden Markov models. And what unifilar means is that if I know the state and the symbol, I go to a unique next state. So graphically, here we go. So if I'm in state A, and I know that I saw a 0, I know I'm going to C. A, when I see a 1, I know I'm in D. This is a little bit kind of a funny case. Independent of seeing the 0, 1, I'm going to go to B. That's okay. That still fits in with this. And then unifilarity has a certain constraint, puts a certain constraint on these symbol labeled transitions. Namely, again, kind of restating what I said here. If I know the state and the symbol, then the state I go there with probability 1. Or the other way to say it is if I know the state, then my uncertainty over the next state and the symbol is the same thing as the uncertainty in the symbol I'm going to see. Yeah. So, and actually, and those people that have studied some formal language and automata theory, unifilar is the vocabulary from information theory. If you study automata, these are deterministic automata. So, the use of the word deterministic here is this interesting collision, vocabulary collision between two fields. What is meant in automata theory is if I am a little machine like this, finite set of states like this, and I'm reading data in. As I'm reading the data in, it's the data, zeros and ones, off the tape, is telling me which state to go to uniquely. That's all it means. For us, it has a different set of sort of consequences, but it's similar. Unifilar means that there's, if I'm reading a binary sequence, I follow a unique state path. So think filament. It's a sense of unifilar. Or if I generated a sequence, there's a mapping, not too complicated a mapping between the state sequence and the sequence generated. So this is actually letting us deal a little bit with this ambiguity that I introduced just before between I'm observing a symbol and the possible many, many, many internal state sequence that could have produced it. Unifilarity constrains that. And I'll give some examples. Just to drive the point home, of course, there are these other things constrained, non-unifilar, that don't have that property. So, and all we need is just one violation anywhere in a state-based hidden model like this, so that if I'm in state A and I see a 1, I don't know what state I go to. There's some uncertainty in that. And you can see, as an observer, this is not good, right? If you have a model that has this, suddenly, and then you measure a 1, your ambiguity, your knowledge about the internal state distribution just got worse, right? So this is going to be, non-unifilarity is going to be one way in which the sort of observation function can throw important information away. In many cases, it's recoverable. So, right. So non-unifilarity leads to this multiple edge paths or state sequences to a single observed sequence. So I'll give some examples of this. Not just talk about the general case. But first, kind of go back through these different processes and see what they look like in terms of unifilar hidden Markov models. Fair coin. Well, a fair coin, we can represent that with a single state. And now the observed symbols are heads and tails. So I put those on the edges. And then I have transition probabilities of 50-50. So there's a little hint of where we're going with this. Notice this is an even simpler model. Before, when I had a Markov chain model of the fair coin, I had two states called heads and tails. And I was kind of confusing the observations, heads and tails, with having some kind of state memory, either here or here. But in fact, the fair coin has no dependencies between them. You know, the coin flips are independent. So here we have a simpler model. There's a single state. We have to think about what a state means here. And then it can, from that state, I can generate either heads or tails with fair probability. And the transition matrix is kind of trivial here, just one. It's a one-by-one matrix. The symbol labeled transition matrices are also one-by-one matrices, but now they have components half a half, which of course, if I sum them back up, I get the internal state transition. Bias coin as a unifilar hidden Markov model. I can also do it with a single state. Well, I guess I forgot to point out, why is this unifilar? Same argument as for the fair coin. If I know the state I'm in, and I know what the symbol is, I know what state I'm going to. Trivial observation. But now the bias coin is, in this presentation, very simple. It also has just a single state. It just turns out having a single state is reflecting the fact that it's an IID process. So IID processes in this have just single states. They're kind of structurally trivial processes. The whole class of IID processes. So that's another benefit we get to labeling the edges with the symbols. Okay, golden mean process as a hidden Markov model in the unifilar presentation. So here's how we do it. We have two states, A and B. It's almost easier for me to describe the label-directed graph. Two states, A and B. If I'm in A, I see a 0, I go to B. But if I'm in B, I see a 1 with probability 1. Whenever I'm in A, basically it's a fair coin flip for a 0 and 1. On 1, I go back to A. On 0, I go to B. Now, so this is a two-state presentation of that. And here's the sort of one way of labeling that, which I just described. I have this output binary alphabet, and I split the state-to-state transition matrix into these two pieces. So there's only one transition on a 0, so this T0 matrix just has this 1/2 probability corresponding to this right here. And then both B and A go back to A. B on probability 1 and A on probability 1/2. So now we can ask this question, if I'm looking at 0-1 sequences, what do I know about the internal states? Okay. So there's just a little bit of ambiguity in the output sequence. In particular, it depends on where you start. So the mapping from internal state sequences to observed sequences over the binary alphabet, it's a 2-to-1 mapping. You can see this here. So imagine that I've seen a series of 1s. I've observed that. Well, either I could have started in B and produced, say, 1 and then 4 1s, or started in A and just produced 5 1s. So we just have, at the initial time, a little bit of ambiguity, kind of finite ambiguity in terms of the output sequence. Well, that's not too bad. So the other thing about this presentation of the golden mean process is that one question we're interested in as an observer, if I know this model and then I come into the lab and I've kind of forgotten what's going on, I want to know what the internal state is. So notice the golden mean presentation here. If I see a 0, I know immediately that the process is in state B. And if I see a 1, I know it's in state A. So we say that the observer is synchronized. So imagine you have some big multi-state process. You're observing this very impoverished 0-1 string, and you want to know how much information I need to, observed information I need to determine uniquely what the internal state is. This case is very simple. One step, I know exactly what the internal state is. Well, let's compare the internal state sequences with the observed sequences here. So we have AB's, internal state sequences, and I metrized it using A as 1, B as 0. And it's the golden mean process that we saw before. It's an internal Markov chain, just the golden mean. Now the observed sequences, turns out they're exactly the same. Well, that was the claim, that rather than using this observed Markov chain, we used a hidden Markov unifilar presentation of it, and the output word distribution looks just like the internal state sequence distribution. So the information is preserved. The internal state information is preserved in the observed sequences. Now this is kind of a simple case here. You could have concluded this from the previous discussion, previous slide, but this is actually sort of a calibration for some interesting things that will happen. So let's look at the even process as if it was a hidden Markov model, and we'll give a unifilar presentation of that. So we're going to have two internal states here. Again, it's unifilar. A goes to A on just a 0, A goes to B on a 1, and B I must go to A on a 1 with probability 1. So the internal structure here, if I just drop the observed symbols, is just the golden mean process. Right? This is the no consecutive B's process, internal. And with all the golden mean probabilistic properties. And state A with probably 2/3, state B with probably 1/3. So now we have this observation process. Split the internal state matrix into these two here. Right? There's only one transition on the 0 back to A. So we just have that one entry here. And then T1, A goes to B with probably half, and then B goes to A. B goes to A with probability 1. So let's go through this again. Compare the internal state sequence. There's one realization. And then you can just follow this through here. So A goes to A on a 0, A goes to B on a 1, B goes to A on a 1, A goes to A on a 0, and so on, and just write out the sequence. And what you notice is that the output binary sequence has this property I alluded to before, and that whenever 1s occur, they occur in a block of even number bounded by 0s. So that should strike you as slightly odd. Why? Because the internal process was just the golden mean. It has like a one-step restriction. Don't produce 2 0s in a row. End of story. That verbal description completely characterizes the golden mean process. And here we have an output sequence which actually has a property that can extend over an arbitrarily long block of 1s. That's evenness. So the output sequences sort of look like this. 0, block of 1s of even number, 0. So somehow this even process, and it's being made more explicit when we write down this unifilar hidden Markov model presentation of it, has an infinite range kind of memory. It can't put an odd number of 1s there. It can't do that. Even if it's seen a million 1s in a row, it's going to put it. When it finally puts the 1 down, so we have an even number, then it can put down a 0, but not before. So this is curious, very curious. Before, with the golden mean, I could describe the structure in the support as we went to longer and longer words by just saying, oh, it's just cleaving out all those words with 2 0s. So that's called its list of irreducible forbidden words. It says one word, don't produce 2 0s in a row, end of story. The even process has a countable infinity of these irreducible forbidden words. At length 3, I see 0, 1, 0. That's an odd number, not allowed. And as soon as I see that, there'll be a cascade through longer words that have this little length 3 subword, and those will all be inadmissible. Those will all be cleaved out. But then, as soon as I start looking at length 5 words, there's a new forbidden word. Right? 0, 3 ones and a 0. Right? This word isn't forbidden by this one. No, that's fine. It's new. And then this word, as soon as it occurs, it also has this cascading effect of cleaving out longer and longer words that contain it as a subword, and so on. So this is the strange thing about the even process. The most dramatic way to state this is that there's no finite order Markov process that can model the even process, or I should say, no finite order Markov chain can model the even process because of this property. So one conclusion is that finite Markov chains are a subset of hidden Markov models. So as soon as I start looking at what classes of processes hidden Markov models can represent, suddenly there's a much wider class of processes that can be finitely presented. And this has, the observable consequences. So here is, again, the sort of internal state sequence words. Well, we know what this is. This is the golden mean, right? No 2 zeros, 3 zeros, 2 zeros and 1, 1 0 and so on. All preclude. So that's what the internal state process is. But now we look at the output, which is the even process. And we see that all the words at length 1 occur, all the words at length 2 occur, and finally, at length 3, we see 0, 1, 0 being precluded. Now you have to kind of imagine along with me, just like the argument I made before, that 0, 0 is cascaded through all the way to infinite sequence, precluding their own Cantor set of forbidden words. That single word has partial responsibility for the structure of the support and distribution of longer words. And then these words here, you have to, well, you can look at the notes and convince yourself that the length 4 words that are forbidden all come from having 0, 1, 0 in them. Then at length 5, up here somewhere, there's 0, 3 ones and a 0, along with other words that are precluded by this one. But then now we have this new length 5 forbidden word, and it cascades down and causes another Cantor subset of support to be precluded. These are just two-state processes. We have a countable infinity of these Cantor sets, self-similar sets that are precluded, and, goes without saying, complicated probability amplitudes. Why is that of concern to us? Because if I just gave you sequence data, this is what you're going to be working with. And the question is, how do I go from this data that I've given you with all these kind of competing kinds of complication, potential structure, how do I go from the data back to, oh, it's a two-state model that's unifilar hidden Markov? So that's spring. I will give you a positive answer in spring. I know I keep saying this, but. And just to kind of stir the pot a little bit, and also so we don't now we're thinking too much right now. You can ask, well, okay, you've been talking about unifilar processes that can be represented by unifilar hidden Markov models. What about the sort of general case? So hidden processes that can be, well, not represented by them, namely non-unifilar hidden Markov models. So here's one example. Call it simple non-unifilar source. And I'm going to draw the contrast as starkly as I can. The internal state dynamic is going to be a fair coin. Okay, so internal fair coin. We have two states, A and B. Again, if you forget the observed symbols here, it's just 50-50 on all the transitions. So all A-B sequences occur inside. But then I'm going to choose a certain kind of labeling of the edges for the measurement symbols this way. So A goes to itself and B on a 1. That's where the non-unifilarity is, right? State, I see a 1, suddenly it becomes ambiguous. I knew I was in state A, but now after I see a 1, I can be in either state A or B with equal probability. I, the observer, just lost information. However, if I'm in B and I see a 0, I know the process is in state A. Okay, so that's it. Unifilar transition, state transition leaving A are the non-unifilar ones. So let's just imagine, I tell you, you just saw a sequence of 20 ones. What internal state sequences could there be? Well, it turns out you can just sort of start enumerating these things. There are a huge number of them. In fact, you can ask how many sequences go to the all one sequence, and it's an infinite number, right? So if I can produce all ones, well, I can just stay in A, or I can stay in A once and then go to B and stay in B, stay in B twice, go down here twice, and so on. You can just kind of enumerate all these possibilities. It's a huge degeneracy now if you see all ones. You really don't know what's going on with the internal state sequence. Now, there's a question. We have this simple non-unifilar source, this process, or this property generated by this particular thin Markov model. Is there, even though this is non-unifilar, is there a unifilar presentation of this? And the answer is yes. I will show you. You will calculate this on your homeworks. There's a way, it's a different presentation. It actually has a countable number of states. But when you write it down, there are a whole set of properties we can calculate that we can't calculate given this model, this presentation. Simple things like how random are the zeros and ones. Called the Shannon entropy rate. You can't calculate with this, but you can with the given presentation. And then again, just kind of visually to make this as stark as possible. Fair point, right? All words are the same length, have the same probability. Oh, here, this is the analytical version of that. Now, so this is over the AB sequences. Now, over this observed 0-1 sequences. I mean, you can't, obviously, how I label the edges, if you want, think of that as some measuring instrument on the internal transitions and states. So the way I labeled that, the way I'm measuring it, it leads to all this structure. No structure internally. All sequences occur, and here things are being included. 0, 0. Turns out that this looks a little bit like the golden mean in its support, but there's very complicated probability amplitude modulation here and so on, and everything kind of piles up down here. Seeing all ones, in fact. Okay, so this is just a very kind of quick tour of how to think about the space of processes, trying to use these word distribution mosaics to give you some idea of the challenge we have when we try to go reverse the process and go from data back to it. Ultimately, and this should remind you of what we were doing with the dynamical systems, there's a classification of processes. So this is a very popular activity in formal language theory to talk about how different machines can recognize different languages. The same thing here. We have a similar kind of hierarchy, which is exactly how the talk was organized. We have a sort of uniform processes, IAD process, R block, Markov, order R Markov, unifilar, and then non-unifilar. So, and what I mean here is that every process that can be represented by an R block process can be represented by a Markov process, and so on. Every unifilar process can be represented as a non-unifilar one. And then there are more processes. Right, so these are the examples we just went through, illustrating each of the categories. And just as a final slide, I already kind of stepped into this. There are two ways to think about these models. So it's the last slide. Either we can think of them as generating sequences, and that was sort of the way I was talking about before, the simple non-unifilar source, non-unifilar source, it's a generator, and then I'm the observer, and I've seen ones, and now that's sort of, now what the internal state sequence is sort of ambiguous to me. So we can think of a process as being generated by a model, and when we do that, the edge label, we put the transition probability first, and then the symbol you see afterwards, just to kind of remind us that this, when I put this down, this is in generating mode. So it produces sequences, word distributions, and so on, or in recognition mode, which is more the way finite state machines and automata models are used in formal language theory. And when we do that, we reverse the, the labels on the edges. We have the observed symbol, what's being read in, and then the transition probability. Now, what does recognition mean for a binary sequence? Well, first of all, in formal language theory, it means that this machine will recognize a word when the path that the word forces the machine to take has allowed transitions. You never run across a disallowed transition. Therefore, if I saw 1, 0, I could not see a 0. 1, 0, 0 would not be accepted by that model. In addition, we're talking about word distributions. So not only are we recognizing which sequences occur, the subject of formal language theory, but their probability. And so we have in the back of our mind the probability of seeing 1, 0, 0, well that's 0, probability of 1, 0, 1. And we calculate that by multiplying together the transition probabilities as we follow a path. Okay, so the connection with computer science is here. Not only do we think of these hidden Markov models as recognizing words like finite state machine does, but also representing the distribution with which they occur. And that can be, if we change the transition probabilities, it may not calculate the right word probability, and then we would say the word wasn't, the stochastic language was not recognized by that machine. Or we use them as generators. Sort of like the way we were thinking about dynamical systems. They just behave, and we observe them. Okay, that's it. Like I said, the Z-transform slides, you can ignore those for now unless you're interested in how to calculate the evolution of state distributions on these stochastic machines. We'll just do some simple examples by hand rather than develop this contour integrals and all the technology behind that. Any questions? Puzzles? Yeah.
In passing, you said that it was possible to create a unifilar model for the non-unifilar order that you presented.
Right.
And then subsequently you showed hierarchy and
right.
the unifilar was outside. So was that just a unique instance of one that could be done and not a suggestion of any kind of general, which would be
right.
in contradiction with the slide?
Yeah, that's a good question. Yeah, so that the classification scheme here maybe should emphasize finitely represented. And so that's the out. For the simple non-unifilar source, it turns out there is a unifilar presentation of it, but it has an infinite number of states. And when we're doing these classifications, you have to kind of be careful whether you allow infinity or not. So these are all finite. This is the space of processes that can be finitely represented. No, that was a finite state in Markov. Right, so in some sense, just if I allow this category to have an infinite number of states, and it turns out the SNS has a countable infinity of states, but there are other non-unifilar hidden Markov models that have unifilar presentations that have a continuum, Aleph 1 set of states. So we'll get there. I mean, I'm kind of jumping it. We don't really have the techniques, the vocabulary yet to do that, but this will all become very clear.